Welcome back. We're going to talk some more about least squares today. Let me remind you what we did last time. So we had a typical least squares problem, let's say in two variables. So we have a matrix, an n by 2 matrix like this, and we're trying to solve ax is equal to this vector c. I've changed the names of things a little bit. Trying to solve ax is equal to c. And maybe we can solve it, maybe we can't, but in any event, A is a map from R2 into Rn, and the picture is the image of A is a plane inside Rn, and this vector C is some point, and if it's not on the plane, what you try and do is find the closest point in the plane to C, and that's this AX, and the error, of course, is the length of this error vector, and its squared length is this number a1 x plus b1y minus c1 squared up to and so on anx plus bny minus cn squared, and that's the least squares measurement. That's what you're trying to minimize. And we saw how to solve this, which is to take the vector x to be this vector A transpose A inverse, A transpose C. Okay, so that was just a review of what we did last time. Here's a key application. It's called least squares fitting of data. And this is an important application in experiments. So the picture is the following. Let's say you've done an experiment and you've made a bunch of measurements. Let's say you've made n measurements, and let's say, for example, that you're measuring things at different times. So at time t1 you've made a measurement b1, and so on up to tn and bn, and altogether this gives you n points, t1, b1 through tn, bn. And suppose we expect that these points are supposed to lie in a straight line, and you're trying to figure out what straight line that is. So you know from the information about the experiment that it should be lying on a straight line. So you put the t's along the x-coordinate and the b's along the y-coordinate, and maybe it looks like this. And, well, if everything was perfect, these would lie on a line, but of course this is an experiment, so it doesn't. They lie approximately on a line, and the question is, what's the best line, the best fit for a line? Well, it looks something like this, and we're going to minimize the error. And, well, let's minimize the least squares error, and what that means is you want to minimize this sum, the sum of the squares e1 squared through en squared, where the ei's are the distances from the points to this line. Okay, well, we know exactly how to do this, so let's look. So here's our line L, and it's a line, so it's given by some equation c plus dt, where c and d is what we don't know. We need to pick the slope of the line and the y-intercept, or however you want to think of it. And if we had an exact solution, that would mean that b1 is equal to c plus d t1, and bn is equal to c plus d tn, and so on. And that is to say, we'd have this matrix equation. Put a bunch of 1's in the first column, and then t1 through tn in the second. And if you multiply those by cd, you're supposed to get b1 through bn. So there you go. This is exactly a least squares kind of problem. Here, the unknowns are these two numbers cd, the parameters of the line, and these t1 through tn are what we're given, and similarly the b1 through bn. So, of course, we solve this by the least squares method. We have this matrix A, and we solve for CD is equal to A transpose A inverse times A transpose B as usual. Okay, now I want to say a little bit more about this. So the least squares picture is that we have this map A from R2 to Rn, because CD is R2 and we're B1 through Bn are in Rn. And the image is this two-dimensional plane inside Rn, and this is the point that we're looking for. So that's how we think of this as a least squares problem. And I want to put in a big caution here. These two pictures are not the same. They're rather different. The two pictures being this one here with the line in it and this one here with Rn. So notice that up here the picture is we have a line in R2, whereas down here we have a plane in Rn. It's just a very, very different picture. I suggest you pause here and think a little bit about the difference between these two pictures. Up in this upper left-hand corner we have a plane, and the b's are the y-coordinates, whereas in the lower right-hand corner we have an Rn, and the b's are giving you a vector in Rn. Okay. In any event, there's no reason that you can only you have to limit yourself to fitting a line. We could do quadratic fits as well. So that is to say, suppose I gave you these n data points and I thought that they fit on a parabola. I could try and find the best parabola to fit. And how does that work? Well, a parabola is given by a quadratic, c plus dt plus et squared, and I want to find c, d, and e now. So before c and d were in R2, and now c, d, and e are going to be in R3. That's the difference. So the points that we get are these. B1 is supposed to equal c plus dt1 plus et1 squared. So if you write this out as a bunch of, as a matrix equation, it looks like this. We're trying to solve this equation. This a times CDE is equal to the vector b1 through bn. So notice the difference now is I have a third column with the ti squareds in it, and I have 3, CD and E is a 3 vector. So now I'm looking at a map from R3 into Rn, and I'm trying to solve the least squares problem here. And it's really the same technique, using R3 instead of Rn. And one thing that this example clearly illustrates is that that red line in the previous example doesn't need to be a line. It could be a curve, a parabola, or anything else. So let's look at one other example along these lines. We don't even have to use just polynomials. We can work with other kinds of functions. So let's see, well, what did I do? I looked first of all at linear least squares, and then I looked at quadratic least squares, and this generalizes in an obvious way to trying to fit an arbitrary nth degree polynomial. And, well, there are other possible functions. For example, this is very close to one that's written in the book. Suppose I was trying to fit some data to a sum of exponentials, e to the lambda t and e to the mu t. And I'm trying to find these constants c and d. I'm just illustrating that it doesn't matter that these functions are polynomials or powers or anything. What do you get in this case? You get, you're trying to solve b1 is equal to c e to the lambda t1 plus d e to the mu t1, and so on. And if you write this down as a matrix equation, you get this matrix here with these exponentials in it, and you're trying to solve this. So again, it's just a least squares problem. It's just that the matrix A is rather different. It looks complicated. It's got exponentials in it, but the t's are given and the lambda and mu are given, so this is some constant matrix, and this is a standard least squares problem. In particular, it's linear algebra. It's not some crazy nonlinear thing involving exponentials. Okay, that's a good place to stop. I will see you in class.